explain what we're going to do today. Let's have a seat. All right, so yesterday we started talking about these other kinds of proofs. Let's slow down. People can hear better if I'm the only one talking. All right, so we started talking about these other kinds of proofs. I asked you to do the first half of that practice packet, 1 through 4, and I'm going to have you do the last part of it today, 5 through 8, but we're going to go through some more notes and examples, spending more time today on the indirect style of proof, which is like contrapositive, which we did, and contradiction, which is where we ended. This is the one that I showed you in like the last 5 minutes yesterday. But I want to go back through this to give you a chance to ask any questions if you want to make sure you understand the logic behind proof by contradiction. Then we're going to do a couple more examples of that. We're also going to do one example that includes looking at cases, because sometimes that comes up. I know it came up at least once in the first set that you had to do, but it'll come up again. And also talk about counterexamples. I think the very last question in the packet has you using the idea of a counterexample to show that something is false. Counterexamples are not relevant when you're trying to prove something is true, but if they give you a statement and say, show that this statement is false, or sometimes they might say, here's a statement, and decide if it's true, you're going to provide a proof to it, but if it's not true, you don't prove that it's false, you just show a counterexample, okay? So that'll be at the end of today. Because this takes a little bit of time, and I want to give people a chance to ask questions, people in the classes before you had a bunch of questions to ask about this. I'm going to wait and check the whole packet together, as I'll check it as 2 homeworks, like 1 to 4 is one homework and 5 to 8 is another, but I'll do that tomorrow, not tomorrow, Friday, when we next have class. And that's when I'll also give you credit for the paper 3 practice that I left for you on Monday. So on Friday, I will first go around and give homework credit for those 3 assignments, the paper 3 practice from Monday, and then the 2 parts of the proof practice. And Friday and Monday I have reserved, we don't have to do any new content on those days. I want to use that to go over questions you might have, first on the proofs packet, because that's relevant for the next test we have. The proofs test, the whole unit test on proofs, is a week from Friday, next Friday, the 11th, okay? So this Friday and Monday, I'll first want to answer questions you have about any of the stuff you've worked on in the proofs packet, and then I do want to go through with you that paper 3 practice that involves complex numbers and like forming the polygon with all the roots of 1 and stuff like that. That was a problem that was on an exam recently. I think it is one of the harder paper 3 questions. They're not all, if you found that to be hard, I don't think you would be alone. And I think most people who did that question on that year's test probably found that to be hard. They're not all like that. But the reason I wanted to show you that one in particular, I want to show you like a range of those paper 3 style questions. We don't have all that many to look at because they've only had these questions since the test got revised in 2021. But the reason I picked that one in particular was because it is connected to stuff we've already done. Like there's complex number connections in that one, okay? So Friday and Monday will be days to go over those 2 things, okay? All right, so let's start here with this. This is the one we're trying to prove that if a squared is even, then a is even. On the previous slide, I proved this using the contrapositive, okay? The contrapositive method and the contradiction method are both under the umbrella of indirect proofs as opposed to direct proofs. In direct proofs, you start with the givens and you say these are true, therefore something else is true, therefore something else is true, and you kind of just make a chain of true statements that hopefully ends with the thing you're trying to prove, right? With indirect proofs, you don't do that, okay? The contrapositive version, which we already did, is useful if you're given an if-then statement and asked to prove that statement. What you're actually proving is that the conclusion has to be true if the hypothesis is true, right? So the if part is your givens, and you're trying to get to that. If you do the contrapositive, you first form the contrapositive, which we talked about yesterday. That means you make both changes to the if-then. You switch the order and you negate. And then you prove the contrapositive directly, right? You now have a new if statement with new givens, right? So those are your givens, and you do the direct method on that statement. At the end, you're getting the conclusion of the contrapositive, and then at the very end of that, once you've proven that the contrapositive is true, you should have one statement that says, because we proved this statement, the original statement, which is the contrapositive, has to also be true because they're logically equivalent. That's all you need to say to like connect them. Shreyans.
And where should cases, would it be better to use the contrapositive rather than the direct?
I don't know if I can say like, I don't know if there's like a neon sign flashing that's going to tell you to do that. I showed you yesterday like one signal that indirect proof is helpful is if you try direct and you get stuck, right? Like that's what happened with this. We tried to prove this directly and we said a squared is even, that means a squared is like 2k. And then I'm trying to get something about a, so if I start with my equation on a squared is equal to 2k, and I want to get to an equation that involves a, I'm going to have to take square roots. And if I take the square root of both sides of the equation that started out a squared equals 2k, I get a equals root 2k. But I'm trying to show that a is even, which means I need to show that a is equal to 2 times an integer. And if I have a equals root 2 times root k, I don't have a 2 there and I don't have an integer. So I'm like not getting anywhere. So one of the reasons why you might prove something indirectly is because direct doesn't work, okay? But more common on the exam, they're going to tell you, prove by contradiction, whatever, or prove using the contrapositive, okay? That's typical. Like when they're testing on indirect proof, usually the idea that you would have to figure out to use indirect is not what they're interested in testing. They want to present you with something and say, use one of the indirect methods on this and see if you understand what that means to do. So probably there's not going to be a lot of cases where you have to first decide that that's the appropriate way to go. Now, in terms of, there's 2 indirect methods, right? There's contrapositive and there's contradiction. And in terms of which one of those is appropriate, again, you might be told, like, prove this using contradiction, prove this using the contrapositive. One thing that helps if you have to decide about which one of those is, they both generally will work. If one works, generally the other one works. But if the thing that you're being asked to prove is not phrased as an if-then statement, then it's not, if you don't start with an if-then, it's hard to like make a contrapositive when you didn't already have an if-then to begin with. So this one has that. That's why this one is pretty easy to do both ways, and that's why I'm showing it both ways. The next statement we're going to do isn't phrased as an if-then, and so I'm not going to do the contrapositive way. I'm just going to do proof by contradiction. Okay? I think there was another hand that went up. Mael, were you asking something? Were you
I was
asking?
going to ask if you can only use this if like the answers are like binary, so like odd or even, or irrational versus non-irrational versus rational.
No, like I think in the practice you have to go through an indirect idea when you're showing that like something's not a multiple of 3. So that's not one or the other. Like if something is not a multiple of 3, does it make sense? There's 2 alternatives there. Like there are 2 different ways that you can not be a multiple of 3. You could be 1 more than a multiple of 3 or 2 more than a multiple of 3. That's different, right? And the way you would represent it is different, right? If something is odd or even, like even means it's 2 times an integer, odd means it's 1 more than 2 times an integer. So like every odd number can be represented the same way. But multiple of 3 or not, you have 3 choices, right? There's like 3k for a multiple of 3, and then not a multiple of 3 could either be 3k plus 1 or 3k plus 2. And if you're having to like if you were going to try to prove that something is a multiple of 3, and you're going to start out by assuming it's not a multiple of 3, that would lead to 2 cases. That's kind of what we're going to get into a little bit later with the case idea. Like when you say assume something is not a multiple of 3, there's not just one way you could write it, right? That means it could be written either as 3k plus 1 or 3k plus 2, and you would have to deal with those 2 things separately. Like let's say it's 3k plus 1, go through and see what happens. Hopefully you get a contradiction. But that contradiction is dependent on the thing being written as 3k plus 1. So you have to treat separately like, okay, well what if it's not a multiple of 3, but instead of being able to be written as 3k plus 1, it's written as 3k plus 2, stuff you did before, now you're doing with a different expression. In that case, you're probably also going to get to a contradiction, but you have to treat each of those as like separate cases.
And if they're both contradictions, that means
If they're both contradictions, that means all that's left, like that means the idea that it's not a multiple of 3, whichever way it was, is not true. So now you're left with, all that's left is it must be a multiple of 3, right? So that would work. Okay, I wanted to clarify a couple things. I know I showed you all this yesterday, but I want to make sure you understand how this looks different from a proof by contrapositive. Notice I don't, even though there was an if-then here, when I'm proving this by using the contradiction technique, I'm not making a new if-then. So there's no new if-then written here. I did not write the contrapositive. Instead, a proof by contradiction will always start out with an assumption statement. In fact, literally the first word you write in a proof by contradiction should be the word assume, right? You're going to say assume that something. And the thing that you should be assuming is whatever is the opposite of the thing you're trying to prove. So if we're being given an if-then here and saying prove this, what we're really saying is if we tell you a squared is even, prove that it has to be true that a is also even. So a is even is the statement that needs to be proven. So you start off with a statement, assume that a is not even. That should be right away. If they ask you to do a proof by contradiction on the exam, and it's like 6 or 7 points or whatever, almost 100% the first point is going to be for having that assumption correct. Like, did you start with an assumption and did you do the right assumption? Did you assume the opposite of the thing that you're trying to prove? Okay? After that, everything else you write can be justified. This statement is not justified, right? You're not supposed to justify the assumption, but everything else you write following the assumption should be justified. So if a is not even, that means a is odd. That means that we could write a as something like 2k plus 1, where k is an integer, right? One more than an even number. So that's what I can say about a. I can then say something about a squared if I have something about a. So a being 2k plus 1 means a squared is 2k plus 1 squared, which comes out to this, 4k squared plus 4k plus 1, which I can write, there's a 2 common to the first two terms here. So 2 times this stuff plus 1. But what do I know about this stuff in parentheses? It's an integer, because it only involves k's and 2's and multiplying and adding. And all of that, if you started with integers, you're still guaranteed to have an integer. So a squared is 2 times an integer plus 1, which means it's 1 more than an even number, so a squared has to be odd. Okay? That is where the contradiction happens, though. Because in the proof by contradiction, you're not changing anything about the if part. That stuff is given. So you were given that a squared is even. In a direct proof, that would have been the first thing you wrote, right? In an indirect proof, you don't start with that. You start with this assumption, but you still have this available to you. You know at any time that you can use the fact that a squared is even. But our assumption has led to this statement, a squared is odd. So now is the time that you bring in, that it's given that a squared is even. That's what creates your contradiction, right? A squared cannot be even and odd at the same time. That doesn't make sense. So if you get to something that's false, a contradiction, then you can say that your assumption must be the reason, the assumption must be wrong, because everything else you've said here is justified. So if you're writing a whole bunch of justified statements following an assumption, leading to something that can't make sense, the only reason you could have gotten to this is because that assumption is wrong. So once you get to a contradiction, if you've only made one assumption and everything else is properly justified, that you're on solid ground to say that assumption is wrong. So now, because we have a squared being both even and odd, and that doesn't make sense, I can say it must be false that a is not even. And if it's false that a is, I know there's a lot of negatives here, but if it's false that a is not even, then all that you're left to conclude is a is even. Does that make sense?
On like an IB test, do they tell you whether to use direct or indirect?
Most of the time, if you were having to use indirect reasoning, they would not only tell you that, but they would tell you the technique. So they would say something like, prove, you will see a phrase, like I'll show you some things that have appeared on the test, but they'll say like, prove by contradiction that, prove using the contrapositive of that, something like that. They also do it with induction, right? You are definitely going to see something that says prove using mathematical induction and then a statement, so you'll know when to use that. If they just give you a statement and say prove that this is true, more often IB uses the phrase show that, but if they say that with no other thing, it's likely you're going to be using direct reasoning in that case. I guess I don't think they've made the claim that like that's 100% true, but based on what we've seen on the test, that's likely to be the case. Leon.
So generally, indirect is after you've already tried direct?
Not necessarily, because if the problem is phrased to you like prove by contradiction, then you're just gonna jump right to this.
Oh, but like if there's, oh, okay. It's already been, sorry, I didn't know this question already.
No, it's fine. I just want you guys to know the idea that, like, in our case, like when I did this, I showed you why direct would not always work, because we did that first, right? And then I went to indirect, and this is a good example to show both versions of indirect, contrapositive and contradiction, okay? But you wouldn't usually exhaust all methods. And for the most part, again, this is pretty new. IB hasn't been testing this nearly as long as they've been testing math induction, right? So it might be we talk all about this, and then you guys take the test this year, and you come back and tell me, like, they didn't ask us to prove anything using contradiction or contrapositive. I would be like, okay, that could happen. Like, there's not an established trend that, like, there's a proof by contradiction on every test. We don't have that many data points on this yet. Okay? If you come back and tell me you didn't have to do any induction, you will see a surprised look on my face. Okay? But if you say you didn't have to prove by contradiction, I would say, okay, that's not that crazy. Like, they're expanding the number of things they can ask about related to proof, but it doesn't mean they're going to ask about every possible thing they say they could ask about on every single test. All right? Okay, let's try another proof by contradiction. So I have one in the practice packet where you're trying to show that some other square root, I think it's root 3, is irrational. Does it make sense that if you have the square root of any positive integer that's not already a perfect square, that's going to end up being an irrational number? Meaning, like, if you look at the decimal approximation, you get like some messy decimal number. Okay? Now, having the decimal go on forever doesn't automatically mean it's irrational, right? If there's a pattern to the digits that go on forever, it's still rational. Like 1/3 is 0.3 forever, right? But that still can be written as a fraction. So 0.3 forever is a rational number because it can be written as 1/3. Okay? Sometimes the pattern takes a lot of digits to repeat. Okay? Like 1/7 is a repeating decimal, but it takes 6 digits for the pattern to repeat. It's like 142857, and then it keeps going. Okay? So there could be some number where you look at the decimal approximation and you're looking at like the first 10 digits and you don't see any pattern, but maybe the pattern is like 15 digits long, right? So you wouldn't recognize it unless you saw way more of the digits. So just having the decimal go on forever isn't enough to conclude for sure, like, oh, there's no way to represent that rationally. Rational means it can be written as a fraction, right? So if you look at the root 2 decimal approximation, like, it doesn't suggest that it is rational because you don't see a pattern there, but that doesn't prove that it is actually irrational. So we're going to prove it, and we're going to prove this using the contradiction technique. And notice here, I'm going to use proof by contradiction, not contrapositive, because the thing I'm trying to prove isn't phrased as a conditional statement. It's not like if something, then something else. We're just trying to prove that the number 2 is irrational. That's like a simple statement. Root 2 is or is not irrational. We're trying to prove that it's irrational. Okay? So if we're going to do it with contradiction, you assume the opposite of what you're trying to prove. So we're going to assume that root 2 is rational. So that should be your very first statement, right? Assume the opposite of the thing you're trying to prove. So assume root 2 is rational. Then you write down what's true because of that. Well, what does it mean to be rational? Yeah?
Expressed as a fraction.
Right. So we're going to use some notation here. I'm going to say if root 2 is rational, we can write it as a over b, where a and b are integers. Right? Does that make sense? That's what a rational number is. It's the quotient of integers. Now, I have another thing here, which I'll explain in a second. If this was possible to do, if there was a fraction that was equal to root 2, does it make sense that once you know there is a fraction that's equal to root 2, there's automatically actually an infinite number of fractions because they're all equivalent to each other. They're just the non-simplified versions of that fraction, right? So if root 2 was actually equal to 4/3, I know it's not, just go with me for a second. If 4/3 worked, then so does 8/6 or 12/9, right? Any of those. So what we're saying here is, not only can I write root 2 as a over b, I'm not picking a over b to be any of those fractions. I'm saying a over b is the simplified version of the fraction. So it says we can assume without loss of generality that a and b have no common factors. Does that make sense? Like once it's possible to write the fraction, there is some version of the fraction that is the simplified version, and I'm saying that is what a and b specifically represent. They are the lowest terms version of the fraction. So in order for them to be the simplified version of the fraction, there can't be any common factors that a and b have, because if there was one, you could cancel that factor out and you'd get a different value for a and b. Are we okay with that? Okay. That's going to be important because the fact that a and b don't share any common factors is what's going to lead to the contradiction down the road. Because right now we don't have a contradiction. But remember, we're assuming the opposite of what we're trying to prove, so we want to keep writing down stuff that's true until we see something went wrong. And when something goes wrong, then we can say, oh, that assumption that we made is not right, so root 2 is actually irrational. Okay, so I'm going to manipulate that equation. So we start with root 2 equals a over b. I'm going to multiply both sides by b to give me root 2 times b equals a, and then square both sides. So that would give me 2b squared is a squared. Are we okay so far? Now, if you have that a squared is equal to 2 times b squared, that means a squared is even. Why? What does it mean to be even?
Divisible by
2, right, divisible by 2. So it means you could write it as 2 times an integer. Yeah, that's what I have here, right? If a and b are integers, then b squared is an integer. So a squared is 2 times an integer. That's the definition of even. So that would tell me a squared is even. And that means from things we said earlier in the slides, we had if a squared is even, then a is even. We already proved that, right? So now we've got that a is even. Okay? Still no contradiction, right? So far nothing's wrong here. So I'm going to keep going. So I left off with a is even. If a is even, what can I now say that I couldn't say until I said that? What is the statement a is even? What's another statement that follows from that? A is even, so how can I write A? James? A is even, that's where I am. And what can I say because of that? I gotta take one more step now. I gotta keep going until I get a contradiction. A being even is not a contradiction.
Written as 2 times an integer.
Right, A could be written as 2 times an integer. What did I use for that one? M. Okay, so A is equal to 2m for some integer m. Remember, we're bringing in all these integers, right? So when you bring something in and you're going to use the fact that you have an integer there, you got to say that it's an integer. So A is equal to 2m for some m. Okay, any suggestion about what I might do now? I have now a different way of writing A. Where did A show up most recently? It was in that equation, a squared equals 2b squared. So I'm going to go back and write that equation, but replace a with 2m now. Okay? So 2b squared equals, instead of a squared, I have 2m all squared, which is 4m squared. Okay? So that's going to get me to, I have 2b squared equals 4m squared. I can get rid of a 2 on each side of this. Now b squared is 2m squared. Okay, if b squared is 2 times m squared, now I know that b squared is even, right? Because b squared is being written as 2 times an integer. And if b squared is even, just like we made the argument for a, what else is even? B is even, right? B squared is even leads to b being even. Now we do have a problem. Do you see it? What's the problem? James?
You can simplify?
Me-
You can simplify b over a.
Right, we had a over b.
A.
Right, we had a over b. We said it was the simplified version. There are no common factors. But if a and b are both even, what common factor do they have? 2. We said they didn't have any common factors, so that contradicts something we already said. So that's the contradiction. If a and b are both even, they have a common factor, 2. That contradicts the statement we made before that said that a over b was the simplified version of the fraction, so they can't have any common factors. So now we have that a and b don't have any common factors, and at the same time they do share a common factor 2. That doesn't make sense. That's the contradiction. That's what you need to be able to say your assumption, which was root 2 is rational, is wrong. And if it's false that root 2 is rational, then it's true that root 2 is irrational. And that's the end of the proof. Francis.
Can we explain one more time at the beginning why we said A and B don't have any common factors?
Okay, let me go back to where I said that. I'll go back in 1 second. When I wrote here, so the fact that it's rational means I can write root 2 as a fraction, a quotient of integers. But if this is possible, there's not a single fraction that represents this. There would be an infinite number of fractions. Because if I can have one fraction here, I can multiply top and bottom by anything I want and get another fraction. So once this is possible, there's an infinite number of fractions that would all be equal to this. And I'm reserving the name a over b to be the one that everything's been simplified already. So I'm being arbitrary there, but as long as root 2 can be written as a fraction, there would be a simplified version of that fraction. And I'm reserving the representation a over b to be the fraction has already been simplified. That's the one. Okay? So if I'm saying a and b is a over b is a simplified fraction, by rule they can't share any factors. Right? But then I started manipulating this equation and got to that a is even, and a is even led me to, on here, b being even also. And if a and b are both even, then they do share a factor of at least 2. And that contradicts the thing I said before, that they don't share any factors. Okay? Are we okay with that? You guys in the practice have a similar thing to do with root 3. And with root 3, you're going to deal with the same kind of thing, except you're going to be dealing with multiples of 3 instead of even and odd is like multiple of 2 or not. You're going to be dealing with multiple of 3 or not. And with multiple of 3 or not, you're going to have this case idea. But our next example has some cases in it, so you'll see how to handle that. Okay? Is everybody okay so far? Ria?
So on an exam, do we have to write out like this entire explanation, or is the math enough to show? Like,
you're going to need some words. You don't necessarily need word for word what I've got on the screen, but if you stripped away all of the words here and only had the equations, it wouldn't follow it up. Like, it wouldn't be clear enough to the reader.
Right.
Okay? So the slides are here for you on Canvas, all right? So if it's annoying for you to be writing every word down right now, no, you can always go back to Canvas and look at the slides. And my exact wording is not important here. But you need enough words like linking the mathematical symbols so that if you're reading it out loud, it reads like an argument, right? This is true, and therefore this is true, and therefore this, you know what I mean?
Yeah.
That's what you need, okay? But the actual verbatim words, I'm not going to be a stickler for like, I said this, and you said this other thing. Like if the meaning is still clear, it's fine,
Okay.
okay? All right. Okay, so we're going to do one more example. This is going to be another proof by contradiction, but this one uses cases. I wanted to show you at least one example where we're doing cases. The reason why cases would come up is if you're trying to make an argument about something being true in an infinite number of cases, but the argument you make doesn't work for all of the cases that there are. So sometimes you can say like, this is true in these cases because of this line of reasoning, but if I try to apply that reasoning to all the cases, something's wrong, it doesn't work for all the cases. You can separate into cases where one line of reasoning works here and a different line of reasoning works here, okay? You don't always have to do this. And usually, if you have to break things up into cases, either your work up to that point will suggest what the cases are, like how to organize things, or there would be information in the problem that would help you figure out that you would use cases, okay? You don't usually have to spend a long time thinking about what would the cases be, but the idea that there are cases means the argument you use in one case is not going to work in another case, otherwise you could just combine them all into one, okay? All right, so here's the statement we're going to prove. It's an if-then again. It says if a squared plus b squared equals c squared. Okay, this is another number theory one, and do you remember what I said yesterday about anytime I'm referring to a, b, and c in this context, what kind of numbers are we assuming they are? Positive integers, okay? So if we have a, b, and c being positive integers, and in the context of positive integers, do you recognize what that represents? Where do you see a squared plus b squared equaling c squared? Where does that come up? That's Pythagorean theorem, like sides of a right triangle, okay? Now, in sides of a right triangle, they don't have to be positive integers, right? They have to be positive, but they wouldn't have to be integers necessarily. But in this argument, we're only talking about positive integers, okay? So if we have a squared plus b squared equaling c squared, then the claim is a or b is even. Now let's talk about that for a second. The conclusion is an or statement. The math interpretation of or is inclusive, not exclusive. Do you know what I'm referring to there? So if I say a or b is even, if they're both even, is that part of that statement or not?
Yes.
Yeah, okay. So if I say I have a situation A, B, and C, and it turns out that both A and B are even, that's included in here. The only way an or can be false is if both parts are false, right? You need one part to be true. Once one part's true, you don't really care what the other part is. The or is already true if you've got one part true, okay? If you wanted to say the exclusive or, like one is true or the other is true but not both, that would have to be spelled out. They'd do something like saying then either A or B but not both are even, or something like that, okay? But the default for or is inclusive, okay? So we're going to prove this statement, but let's, just to give you an idea of how this does seem like it's going to be true. We said we're talking about Pythagorean theorem. Can you think of like integer sets ABC that work for Pythagorean theorem? Like what are some that just come up all the time?
3, 4, 5.
Okay, 3, 4, 5. Now in this, does it make sense? The C is determined. Like which one of these is the C? 5. The A and B could be either or, right? It's not important that we call A 3 and B 4. They could be switched. But the idea is one of the two of those at least has to be even. And in this case, the 4 is even, right? What's another triple that works besides 3, 4, 5? 5, 13. What's the other number? 12. So it actually goes 5, 12, 13. Okay, 13 is the C. That's why that matters, right? But 12 is the even one there. Anybody know any other ones?
7, 25, and
That's another one where we're missing the middle one.
24.
24, good.
So,
Okay, and that's even. There's another one, 8, 15, 17. 8's the even one. Okay. I don't know if we want to play like how crazy can we get. I'm a math teacher. I don't have a lot to do, so I can do some other ones. Right, 9, 40, 41, probably not one that's come up a ton of times, but that's another one. 40 is the even one. Now, do you also remember that once something works, any multiple of this also works, right? So that's why I was saying be careful about making sure you understand that, like, that's not saying only one has to be. Like in all of these, only one or the other is. But like 3, 4, 5 leads to 6, 8, 10, right? 10 would be the C, but in this case, they're both even. Like that doesn't disturb that. It's just saying you will not get one where both of the A and B are odd. If that statement is true, then that would never happen. Okay? So that's what we're going to prove. Okay? All right, now we're going to prove it using contradiction. So what is the very first thing I'm going to write? We're going to prove by contradiction. So we begin with, what is the very first word we should say? Assume. Good. Now what do you assume? This one's a little tricky to phrase. Beyond?
Both A and B are odd.
Right. If it's false that A or B is even, you have to assume the opposite of what you're trying to prove. So if that statement was false, A or B is even is a false statement, then the true statement is A and B are odd. Does that make sense? Okay, so that's the assumption. Assume that A and B are both odd. That's the opposite of what you're trying to prove. Okay? All right, then you go from there. If A and B are odd, how can we represent them? A could be 2m plus 1, B could be 2n plus 1. And I'm going to substitute, except I pause here because I forgot something. Not on purpose, actually, sadly. What should I have written? Leah, did you say?
M and N are integers.
Right, I brought in m and n. Those were not part of the problem. And it's important I know that those are integers. I need to say that. So right here, as soon as I mention them, I should say m and n belong to z. You okay there? Okay. Now I'm going to substitute them into the equation. Remember, in a proof by contradiction, you're not changing the if then at all. The if is your given information. So we are given that it's true that a squared plus b squared equals c squared. I assume the opposite of this, and now we've represented a and b this way, so I'm going to put those expressions in for a and b here, and that's what's going to be equal to c squared. So I put 2m plus 1 in for a, 2n plus 1 in for b. I haven't written c squared yet. I'm just manipulating the left side right now. Does that make sense? 2m plus 1 all squared plus 2n plus 1 all squared. You expand that out. You get those two expressions, 4m squared plus 4m plus 1 plus 4n squared plus 4n plus 1. The only thing I can do with that is combine the 1's. So I get a 2 at the end. And then everything but the 2 has a 4 common, so I pulled the 4 out. So I'm left with 4 times something that is definitely an integer, because m and n were. And all I'm doing is multiplying and adding m and n things, right? So it's 4 times an integer and then plus 2. That's what c squared is. Whoops. We okay so far? Okay. Now, remember, with proof by contradiction, you just keep writing true things until you get to a contradiction. So what I have right now is that this thing would be equal to c squared. The only thing I know about c is it's a positive integer. So c squared could look like that, right? That's not a contradiction. So we just keep going. Okay? Now, here's where the cases could be set up in this one. Okay? I'm going to basically make an argument to show that that expression does not make sense for c squared. Okay? That's what my contradiction will be. But the argument I'm going to make about why this can't represent c squared turns out to depend on whether c itself is even or odd. And c was only given as a positive integer. It could be even or odd. And if it's odd, I can make one argument. If it's even, I can make a different argument. I can't make the same argument for both. That's why I'm doing cases here. Okay? So the odd one is simpler. Okay? If c is odd, then c squared is also odd. Now, do you follow why that's true? It's based on stuff we've already said, mainly yesterday, I guess. But do you see this, Shreyas?
Proof, would we have to like reprove that C is odd?
No, so if this was on an assessment, either there would have been an earlier part where you did that, or that information would be given to you in the problem. You wouldn't have to like do it on the side or something like that. Okay? Can you tell me, do you remember we proved if a squared is even, then a is even? That was one of the things we did. And you see that this is the contrapositive of that? Because it's turned and negated, right? So that's equivalent to a statement that we already proved. Okay? Another way of thinking of it is, if c is odd, you could write it like 2k plus 1. And if you square 2k plus 1, you're going to get like an even expression and then a plus 1 at the end. Like that's going to be odd too. Okay? So if c is odd, then c squared is also odd. But if this is how c squared is written, do you see what the problem is with saying that this thing is odd? What's common to all of this? 2. This is 2 times an integer. So that has to be even. But I just said if c is odd, c squared is going to be odd, and that thing is even. That's a contradiction. Okay? But I'm not totally done yet, because this contradiction came from assuming that c is odd, and there was no rule that said c had to be odd. C could be even. So there's like a loophole here that we have to close. Does that make sense? Because I could say, well, what if c is even? Then your contradiction doesn't come up. There's no problem here yet. So we have to address c squared being even, okay, or c being even. If c is even, the argument, if I tried this argument, if c is even, then c squared would be even. But this is even. So that on its own doesn't lead to a contradiction. That's why the argument's going to be a little different in the even case than it was in the odd case. Okay? In the even case, c is even, c would be 2k. So c squared would be 2k all squared. Oh, did I do it again? Have I mentioned k already? No, I don't think I did. So what did I forget there? Okay, make sure you put it there. All right, c squared is equal to 2k all squared, which is 4k squared, right? So that means c squared is a multiple of 4. How do I know that? 4 times what's important on the other piece? Integer, right. C squared is 4 times an integer. So by definition, it's a multiple of 4, okay? But look at what we have up here. Is this a multiple of 4? No. This part is, right, 4 times an integer, but then we're adding 2. How far apart are multiples of 4? They're 4 apart, right? So if you have a multiple of 4, and then you only add 2 to that, do you see you're definitely not at the next multiple of 4 yet? You're stuck exactly in between 2 multiples of 4. So I know for a fact this is not a multiple of 4, c squared. But I just showed that if c is even, c squared is a multiple of 4. So this contradicts that expression. Okay? But the way the contradiction comes about is different depending on whether c is even or odd. That's why we had to have the 2 cases. Okay? But now, in either case, I got to a contradiction. So now, all that's left to say, since things went wrong in either direction, is my original assumption was wrong. My original assumption was A and B were both odd. So if that's false, what is true? One of them has to be even. Okay? That's our end result. All right. Does anybody have any questions about this one? Is everybody surviving here? This is like heavy exercise for your brain, right? Hard thinking going on. Okay, the only other thing I'm going to do here before we go is talk about the counterexample idea. Okay, and this is easier. This is a good thing to end on because it doesn't require nearly as much heavy thinking. Okay, counterexamples are not used when you're trying to show something is true. They're useful if you are trying to show that a statement is false. So if you are given a statement up front and asked to show it's true, you can give a bunch of examples where the statement works out. Those examples, no matter how many you amass, do not make the statement true in general, right? You cannot prove something is true in general if it's true for an infinite number of cases by just checking cases, and you don't really even get closer to proving it the more cases you've shown it works out for, because there's, no matter how many you try, there's still always going to be an infinite number that are left to do. But if you're trying to show something is false, if the claim is something is always true, and you want to say, no, that's false, you only need one single counterexample to do that. Okay? So let me give you an example of that. Here's an algebra statement. Okay? If n is a positive integer, then n squared minus n plus 41 is prime. That's the claim. Now, suppose I gave you this statement and said, this is false, but I want you to justify that it is actually false. So you don't go into like a proof to show that something is false. You just need to provide a counterexample. But a counterexample we talked about, this is basically showing an if-then is false.
Excuse the interruption.
Yeah.
I have Leon for just. Oh,
Okay.
thank you.
Yep. We talked about when you're showing something is false, you need to show something where the if part is true, but the then part is false. So we need a positive integer where this doesn't come out prime. Okay? Now, if n is a positive integer, what's the smallest value of n we could have? 1. If you plug 1 in there, what number do you get back out? 41. And that is prime, right? If you plug in 2, it's going to be 4 minus 2 plus 41, so we're adding 2 to 41, we're going to get back out 43, that's prime.
You also do 41.
Okay, right, you're jumping ahead, but that's the exact right thing to think of, okay? It turns out if you just try to brute force this, like look at every value of n starting on 1, it's going to take a while. It appears this might be true, because it's true for a lot of cases. So instead of just trying to go in order, looking for the first time it doesn't work, try to be strategic about it. Why are you using 41, Maya?
Even the 41s cancel out, and you have 41 squared, which can be prime.
Right, because 41 squared is definitely not prime, since what is certainly a factor of 41 squared? 41, right? So that's the easiest one to use here, is that, okay? So you want to try, when you're looking for counterexamples, you don't necessarily like just start from the beginning. Like sometimes there isn't even a natural order. There is sort of a natural order here, but sometimes even though there is a natural order, that's not necessarily the path to go. Try to think about like, how could I make this thing, if I know it's false, how could I show that? What kind of example could I get? And you want to make use of the 41s canceling out here, right? And then you're just left with the 41 squared, which is definitely not prime. Okay? I think I have one example in the practice packet. I think it's the very last question that says like, give a counterexample to show that this statement is false. Okay? All right, so you have enough now to finish out the proof practice packet. Tomorrow I'll give you homework credit for that, and then we can talk about any ones you want to talk about. And if we get done with that, we'll move to paper 3 practice. If it takes the period tomorrow to do this, we'll do the paper 3 practice on Monday. Okay? But you should bring both of those with you so I can give you homework credit for both things. It'll be 3 assignments altogether. Okay?